Now we analyze coupling into waveguide by diffraction grating. Diffraction grating changes the direction of the incident field by diffraction. This can be interpreted as summing of the grating vector kg to the tangential component of the incident tangential component of the wave number. The grating vector is and the capital lambda is the period of the grating. By this sum, we can construct the diffraction in transmission through the grating as well as diffraction from reflection. For coupling into the waveguide, we are only interested in the transmitted field. We can then write the tangential wave number on both sides of the interface as tangential component of the incident field plus m times the grating vector, and here m is diffraction order. This equals tangential component of the wave number of the transmitted field. This tangential phase matching equation can be written as which is a well-known diffraction equation for transmission gratings. As you see, in case of m equals to 0, we observe the Snell's law. This diffraction equation is often written as for each waveguide coupling situation, it's useful to draw the vector components with their directions. Then it is straightforward to identify their lengths and coupling directions, as well as to solve the desired parameters without trying to memorize the specific diffraction equation. Let's investigate three cases. First, light is coupled to forward direction. If we analyze phase matching of the incident light with the waveguide mode, the tangential component of the incident field and propagation constant should be equal. They can be equalized by suitable grating vector. This phase matching can be written as, and further, the propagation constant of the waveguide can be written as. From this, we can now solve either the desired period of the grating or the angle for coupling a certain mode. In the second example, light is coupled from direct incidence. In this case, waveguide mode can propagate in either forward or backward direction. Phase matching can now be written as, in this case, the tangential component is 0. And the phase matching condition is relatively simple. Now we can solve, for example, for the period. Third, light will be coupled to backward direction. Phase matching can now be written and analyzed as tangential component grating vector, propagation constant with the direction. Let's take a familiar example. Our waveguide has a refractive index of 2. The claddings have indices of 1.7 and 1.0. For this waveguide, we have calculated the effective index of 1.9594 for the fundamental TE mode at the wavelength of 800 nanometers. We wish to couple light in an angle of 51.6 degrees. And our question is, what should the period of the grating on the surface of the waveguide be to enable the coupling into forward direction? We draw the tangential component, propagation constant, and grating vector. Then we identify the phase matching condition and simplify. When we solve capital lambda, and finally we have the period of the grating, which is 680 nanometers.